looking at probability rules, we now want to look at total law probability. And so we're discussing probability rules. We already looked at 6 of those. We talked about basic rule of probability. We talked about complement rule. We talked about problems involving and, problems involving or, finding probability of neither A or B, independent versus dependent evidence. We now want to look at total law of probability. Now let's look at where do we use total law of probability. Now, total law probability allows us to find an unconditional probability. So it allows us to find an unconditional probability of an event. So the key is that you want to find an unconditional probability of an event by conditioning on mutually exclusive and collectively exhaustive events. So this is the key. Where do we use total law probability? Mutually exclusive means no overlap. Collectively exhaustive means the union is sample space. Overlap means you don't share any common outcomes. If two events are mutually exclusive like A and B, the probability of the intersection is a null set. So total law probability allows us to find an unconditional, this is the key, we want to find an unconditional probability of an event by conditioning mutually exclusive and collectively exhaustive events. So if we write down the total law probability, so it would be like this. This is how we mathematically write it. Probability of A is probability of A and B plus probability of A and B complement. And then further using the multiplicative rule, we can write this as probability of A given B into probability of B plus probability A given B complement into probability of B complement. This is probability of A using total law probability. Here B and B complement need to be mutually exclusive, and we know an event and its complement are mutually exclusive and collectively exhaustive. So whatever events you're conditioning on need to be mutually exclusive and collectively exhaustive, and we know an event and its complement are mutually exclusive and collectively exhaustive. Right, so here we want to find an unconditional probability. This is an unconditional probability, not conditioning on anything. So we want to find this unconditional probability of A by conditioning on mutually exclusive and collectively exhaustive events. These can be more than 2 events as well. So what is the application of this? So the application of this is sometimes a problem gives several different conditional probabilities or intersections of an event A or intersections of an event A. Right, so sometimes the problem is going to give you different conditional probabilities or intersection of an event A, but does not give probability of event A itself. In that case, you can use, but does not give probability of event A itself, right? So it's not giving us the unconditional probability. It's not giving us probability of A. It's not giving us this unconditional probability of event A itself. It might give you some different conditional probabilities or intersections of event A, and then in that case you can use total law probability, which says that this can be found as probability A and B plus probability of A and B complement, which can be further simplified using the multiplicative rule as probability of A given B into probability B. So total law probability can be written in terms of intersection or in terms of conditional probabilities, depending upon what information you're given. Right. So if you look at a quick example, so example is event A is accident occurs. Event B is person is accident prone. and say you're given, and we're given probability of A given B is 0.4, probability A given B complement is 0.2, and probability of B is 0.3. And you want to find probability of A, right? We want to find probability of A here. So we're not given probability of A, but we're given several conditional probabilities involving A, like probability of A given B and probability of A given B complement. So using total law of probability, because here we want to find an unconditional probability A by conditioning on mutually exclusive and collectively exhaustive events P and B complement, right? So using a law of total probability, so I'm sorry, probability of A can be written as probability of A intersection B plus probability of A intersection B complement. So this is the probability accident occurs and person is accident prone. And person is accident prone. Probability accident occurs and person is not accident prone. Right, so if we find this and then we can write this as probability A given B into probability of B plus probability A given B complement into probability of B complement. Now all this information is given to us. Probability A given B is 0.4, probability of B is 0.3, probability A given B complement is 0.2, probability of B complement is just 1 minus probability of B using complement 3, because we know the probability of an event is 1 minus probability not event. Probability of B complement is just 1 minus probability of B. And then you can somewhere find probability of A. So here, like we looked at, we wanted to find an unconditional probability of A by conditioning on mutually exclusive and collectively exhaustive events, in this case P and B complement. So we apply total law probability when we're given. Sometimes problem gives us several different conditional probabilities or intersections of an event A, but it does not give us the probability of event A itself. In this case, we were given several conditional probabilities involving event A, like probability of A given B and probability of A given B complement, but we were not given the probability of A itself, so we applied the total law probability.